So here is sort of where we left off. We had introduced the idea of two-dimensional kinematics, the idea that we can think about objects as they move in a plane as having like parts of their motion that are in one direction and parts of their motion that are at a 90-degree angle to that. And because of physics magic, we can use that to help us solve problems that involve objects that are not moving along a line. They're moving along on the surface of a plane that is comprised of two intersecting dimensions of motion. And I had mentioned in the distant past that many of the quantities that we're looking at are what are called vector quantities. So I told you, displacement, position even. Position, displacement, velocity, and acceleration are all what I referred to as vector quantities. We didn't go into the details then. We're going to start going into them now. So the first piece is what is a vector? What is a vector quantity? I gave you this definition before. It's a quantity that has a direction. It's a quantity where it's not just how much of whatever it is that we're talking about that matters, but what direction it's in. The direction part of it is something that we have to be able to express in a way that other people understand. So that direction part of it is perfectly valid if we all are looking at the same thing and we all know what we're talking about, to use directions like left or right or up and down. Like if I am standing here and I say something can move to the right or something can move to the left, you all know what I'm talking about. So those are perfectly valid directions. Or if I were to say, let's say you're up on the football field and you throw a ball straight up in the air, that's a direction. And it makes perfect sense. We can all appreciate it. Other times we have to be a little bit more specific. Like if I give a direction in terms of like, toward the car, which car am I talking about? I need to sort of point, and we sort of need to have some orientation. Typically in this class, our directions are going to be oriented on a coordinate, sort of a standard coordinate axis, where 0 degrees is horizontal to the right, and our angles increase in the positive direction as we move counterclockwise. And this is your standard framework for math as well. So typically, if we were going to look at something like this that has a direction, we might think of this angle right here as being reflective of that direction. That's not always true. We could refer to compass directions as well. In a compass, 360 degrees is, straight up, and so it looks different, right? Like 90 degrees is to the right, and it's not the same orientation that we have when we're using a standard Cartesian coordinate plane. As long as we identify what we're talking about, that direction becomes pretty clear. The magnitude is a little bit more interesting, because when we talk about how big a quantity is, it's not just length that we're referring to. When we talk about vectors, we're going to be tempted to say, well, how long is it? The reason for that will become clear. We're going to draw vectors generally as if they were arrows, but they're not. A vector isn't an arrow. Arrows have length, but not all vectors do. So we don't talk about the length of a vector, we talk about the direction and the magnitude. Those are two quantities that are associated with vectors, and they define the vector. I can talk about vector quantities like velocity. I could say it has a magnitude of 4 meters per second, and it has a direction of 17 degrees on a standard coordinate plane. And now you know how big that velocity is, its magnitude, and you know what direction that velocity is. You've been given a number for the magnitude, and you've been given an angle for the direction. Where things are going to get really confusing, and I'll talk just a little bit about this today, but what's going to happen when we start solving problems is your own arrow drawing is going to confuse you. And the reason for that is because you have used arrows to represent vectors before, which is great because they're super useful for that. But an arrow isn't a vector. When we talk about the difference between a vector and an arrow. A vector is a quantity. A vector is a quantity that has two parts to it. The magnitude, which tells us the size of the quantity, and direction. An arrow is a symbol that we can draw. And arrows have a couple of quantities as well. We can draw arrows of varying lengths, and we can draw arrows on our paper in various directions or at various angles. And the thing about an arrow that's really nice is that we can use this symbol to represent a vector quantity. In that case, the length would represent the magnitude, and the angle of the arrow would represent the direction. And so that kind of, like, the problem with that is that because arrows so naturally fit what we want our vectors to be all about, that we get confused. We point at an arrow and say, this is a vector. And when we think about that, it makes perfect sense, because like this is how long the vector is. It starts here and it ends here, and it's in this direction. Like, what else would we want to know? The thing about arrows is that arrows are very literal representation of displacement vectors. If we think about an object that starts at this position and moves to this position, then this arrow shows the path of the object, the length of the arrow is how far it went, the angle is the direction of travel. That is really easy to understand. When we start using arrows to represent other quantities, like velocity, or acceleration, or force, or momentum, like other things that have a direction associated with them, it gets weirder. Because how long is 5 meters per second? If I tell you that there's a car out on the road and it's driving at 5 meters per second, how long is that? We don't have a length that's 5 meters per second. We might have a vector quantity that has a magnitude of 5 meters per second. We might draw an arrow that has a length that sort of represents that magnitude somehow. What does that mean? Well, that means things like, if this is a vector quantity, if this arrow represents a vector quantity that has a magnitude of 5 meters per second, then a shorter arrow would have a length that represents a smaller magnitude. That makes sense. But we don't measure things in meters per second. I'm not ever going to hold up a ruler to something and be like, yeah, that's about 6 meters per second long speed. Like, that doesn't make sense. And when we think about other quantities, it's the same. When we think about a force, if I walk up to this filing cabinet right now and I push it, it doesn't move. But I sure could draw an arrow that represents my force. It makes a lot of sense to do that. I'm pushing that cabinet this way. If I push with a greater force, then I might draw a longer arrow. If I exert a force in a different direction, like if I lift it up, I would draw an arrow in a different direction. But the thing is, the filing cabinet didn't move. So these arrows didn't start and end somewhere. This doesn't show me how far it went. I pushed with greater force, I pushed with different directions, but those arrows tell me nothing about how far it went. And that's where it gets confusing, because we're going to start seeing arrows, and your brain is trained to see an arrow as the start and the end of an object as it moves. That isn't always going to be the case. So we're going to have to practice that. That's all I'm going to say about that for now. Down the road, we'll see examples, lots of examples, where representing vectors with arrows is going to lead to confusion, because we're going to imagine that these arrows are telling us something about motion when they're not. Okay? Or we're going to specifically imagine that they're reflective of displacement, but they're not. Okay? The skill that we're gonna start working on today, which we're gonna do in a very superficial way, I'm gonna show you a couple of things. There's way more to this, but our basic skill, the simplest way of thinking about it is we wanna take advantage of physics magic, okay? And the most magical thing about motion in 2 and 3 dimensions is that we have discovered that if things are moving on a plane, we can examine their motion in 1 dimension of that plane, and it is completely independent. It's not controlled at all by the object's motion at a 90-degree angle to that dimension. And that works no matter what our first dimension is. So we could look at a dimension that's horizontal, and that means vertical motion is completely disconnected from that. They do not influence each other at all. We don't need to know anything about an object's vertical motion to know how it's gonna behave horizontally. If we tilt our angles, it still works. We can have a frame of reference where our axes are tilted with respect to, like, the ground, for example, and motion along these axes is still 100% mathematically independent. If I know everything about the motion in this dimension, I don't need to know anything about what's going on this way to predict how my object is going to move along this dimension. So that's physics magic. We want to get there. Sometimes the quantities that we're dealing with are already lined up with our axes. Sometimes we know something is moving straight up or moving to the right at a certain time. Sometimes we know an object's acceleration is straight down. Sometimes we know an object's vertical or horizontal displacement in a projectile launch, and that's super handy. But what do we do if we have a quantity that is a vector quantity that is not in the direction of either of our axes that we've chosen? And the answer is, and this is where the super complicated skill is, that we're gonna break it into what we call component vectors. The simple version of that really complicated skill is that when we have the most common frame of reference, which is a set of coordinate axes where one of them is perfectly horizontal, we'll call it the x-axis, one of them is perfectly vertical, we'll call it the y-axis, and the direction that we're given for our vector quantity is an angle with respect to the positive x-axis, then we can figure out how much of the overall vector quantity is left and right, and how much of it is up and down. And we'll talk more about the conceptual piece of that, because what does it mean that it has this much left and right and this much up and down? But visually, you can kind of see it, can't you? This arrow here represents a vector quantity. That vector quantity, if we think about just how much left to right stuff there is, this arrow sort of matches up with it. And if we think just about how much up and down stuff there is, this arrow matches up with that. So we're using arrows to represent vector quantities. Not all vectors have to do with length, but if these were lengths, and if they were to scale, we could measure them. And what we would see is that this vector A has a certain length, and this vector A sub x has a certain length, this vector A sub y has a certain length, and if we line A sub x and A sub y up, then what happens is we end up in the same place as if we started at the beginning of vector A and just went straight to the end. Most of you saw that in the vector simulation activity. Some of you haven't gotten all the way through that, played around with it too much yet, and that's okay, but if you've had the chance, you've seen how this visual mathematics works. If we use arrows to represent vectors, we can add them together by positioning arrows in such a way that they kind of trace out a path, and we can get from one place to the other in a variety of different ways. Our job today is going to be to figure out how long this component is and how long this component is. There's two ways to do that. The hard way is to use trig. You have to know trig, and you have to be able to use it on your calculator. If you know trig, then given this standard reference frame, given an angle with respect to the positive x-axis, then the horizontal component of a vector is going to be the magnitude of the vector times the cosine of the angle. The vertical component of a vector is going to be the magnitude of the vector times the sine of the angle. Those of you who know trig can do that. Those of you who don't know trig, if you're not in AP Physics, you won't need to do that. If you are in AP Physics, you will need to do that. You're going to need to be able to understand the trigonometry involved. But if you're not in AP Physics, we have another way of dealing with this. I have a spreadsheet that I made for you all, and it is in the modules at the very bottom. There's actually two spreadsheets that I'm going to show you today, and they're both down here in the resources. One is called the Vector Solver, and one is called the Kinematic Solver. I call them solvers because they solve things for you. The Vector Solver looks like this, and you won't be able to type in this. You'll need to make a copy, and I always call mine Vector Solver -Regar. So there's my copy of the Vector Solver, and the way the Vector Solver works is if you tell it the magnitude of an angle, like 10 meters per second, and we give it a horizontal angle, like 17 degrees, and we tell it that the vector is in this up and to the right direction, which all our vectors are going to be to start with, then it'll tell us the horizontal or x component and the vertical or y component. It just does the math for you. It does the trigonometry for you. So if we were to look at this vector quantity right here, if we were to identify this length and this angle, we could put that information into the Vector Solver to find the horizontal and vertical parts of this vector. So that's how you break them apart. We'll talk more about that down the road because there's a lot more conceptual stuff. What I want to do is just walk you through an example. When we think about an angled launch, this is one where we're going to need to do some vector stuff. So an angled launch might involve, say, for example, let's say we use the simulation, the PhET simulation. Let's say that we set it up so that the launcher itself is at like a 32-degree angle. Okay? And let's say that our initial launch speed is like 11 meters per second. That's one we can set on there. Right? And then let's say that the ball itself starts like 6 meters above the ground. And we are asking here the same question. How far is it going to go? So we know with an angled launch, it's going to go up first, right? And then it's going to come back down. So it's going to follow a parabolic path, but it's going to go up first before it comes down. And what we're looking to find is how far does this thing go? Okay. Here's how you solve a problem like this. It just involves one additional skill, the Vector Solver, which I've already shown you. And I'm going to give you another, I have another little giveaway for you too that I think will be helpful for at least some of you. So here's how we solve these things. We draw a picture. I just did that. We establish a position 0, 0, which still we do in the same spot that we were doing for a horizontal launch, which is directly below the ball on the ground. And we'll use the same axis of reference. So we're still going to use a vertical axis that we'll call y, a horizontal axis that we call x. Our positive directions are going to be up and to the right. Yeah?
So that's 0.32, that's the angle.
That's a theta.
Oh, theta.
Yeah, sorry, it's not 0.32, it says theta equals 32 degrees.
Okay, that makes
yeah.
a lot more sense.
Yeah. In the steps that I gave you for solving these kinematics problems, there was one that we skipped because we didn't need to do it, and that is to find vector quantities that were not aligned with our reference axis. And this is the first time that we have one. This vector quantity, the speed of the ball as it comes out of the launcher is not either in the x direction, it's not perfectly horizontal, nor is it perfectly vertical. It's at an angle to both of those. So what we're really trying to find out here is, if we think about this 11 meter per second velocity at a 32-degree angle, if we think of it as an arrow, which it isn't, but if we draw it as an arrow, what we want to know is how much of that arrow is left to right and how much of that arrow is down to up, okay? We drew a triangle. There are no triangles here. There's no triangles. Like, this ball isn't gonna move in a triangular path. Like, at any one point, its location, its speed, its acceleration are not triangular. But if we represent a vector quantity as an arrow, and then we represent two components that add together to make that vector quantity that are at 90-degree angles to each other, then all the arrows, if we put them together, will form a right triangle. So that means, those of you who remember the trig, the horizontal component here is going to be 11 times the cosine of 32. The vertical component is going to be 11 times the sine of 32. But luckily, you don't have to know that. We're going to let the vector solver figure that out for us. Our vector magnitude is 11. Our angle is 32 degrees. So that means that our x component is 9.33 and our y component is 5.83. And those are meters per second, because our overall vector here is a velocity vector. So that means the left and right part of this speed is 9.33 meters per second, and the up and down part of this speed is 5.83 meters per second. This object is not moving left and right, then up. It's not making a jaggy pattern. It's just that at the moment of launch, we could think of its speed as having two pieces that are happening simultaneously. At the same time it's moving to the right at this speed, it's moving up at this speed. But that's gonna change, right? So we're not gonna see this ball just move off in this direction. We're not gonna see the ball start here and end here. This arrow represents its speed at a moment in time. As time goes by, that speed is gonna change and the direction is gonna change as well. It's not moving in a constant direction. It's turning as it goes. Okay, so that is a conceptual thing we'll come back to. So how do we use this information? These tell us our initial velocities. This right here we can think of as the overall initial velocity. There's no x and there's no y, because this isn't aligned with either the x or the y axis. This isn't in the x direction or in the y direction. It's in the 32 degrees in the positive direction from the positive x-axis direction. That's its direction. So we can just call it initial velocity. This quantity right here is going to be the initial x velocity. This quantity right here is going to be the initial y velocity. This is how fast it's moving left to right at launch. This is how fast it's moving up and down at launch. Which means we can now solve this problem by using the kinematics equations, the same way that we did before. We have an initial horizontal position of 0, a final horizontal position that we don't know. Our initial velocity in the x direction is this 9.33 meters per second. Our final x velocity, we don't know, except we do, because the acceleration is 0, which means our final x velocity is going to be the same as our initial x velocity. And we don't know how long it moves, we don't know how long it takes to traverse this path. When we look at our y variables, it starts 6 meters above the ground, it lands on the ground, its initial velocity vertically is this fast, upward, 5.83 meters per second. Its final velocity in the y dimension, we don't know. And we talked about this the other day, but this is I saw some people making this mistake because it's so easy to make this mistake. We think, oh, it hits the ground, it stops, which is true. But these equations only work when acceleration is constant. As soon as any object comes into contact with the ground, it is no longer in free fall. The acceleration is no longer 9.8 meters per second squared towards the ground. Our equations break. So when we do this kind of work, what we're really trying to figure out is right before it hits the ground. And right before it hits the ground, this thing is moving down, and we don't know how fast, so we don't know the answer to that. We do know that its acceleration is 9.8 meters per second squared straight down, which is our negative direction. And we don't know how long it took. So we've done problems like this with a perfectly horizontal launch where this quantity was 0. It turns out we solved this the same way. We still don't have enough information to find either time or final position in our horizontal dimension. We have enough information to find either final velocity or the amount of time it moves in the vertical dimension. All we really need to know is how long it's moving. Okay? In general, you may not know that that's all you need to know, but in this particular kind of problem where you're predicting the distance a projectile goes, when you know initial speed, launch angle, and height above the ground, it's always going to work the same. We want to find time. So our values are 6, 0, 5.83, and negative 9.8, and I'm going to show you the second little giveaway here, which is another solver that I predictably call the kinematic solver. And this is, I know, this is the same deal. You'll have to make a copy. I know. Wait till you see this. This is actually, so of all the things I've done in my life, and I include the birth of my 3 children, this is the one thing that I'm actually proud of. They know. So this is, I'm going to play this video for them and be like, yeah, I know, Dad. So this is pretty straightforward. I made it, so it's not, there's some things about it that you probably won't love, but once you get the hang of it, it's super handy. So basically what we can do is just put our values in, our initial position. This is Y stuff, right? This says X, but it's just, this is just one dimensional. So our initial position is 6, our final position is 0, our initial velocity is 5.83. We don't know our final velocity. Our acceleration is negative 9.8. And to find time, I'm going to click this little box here by the t variable. And then the equations, you have to know which equation you would use. So you may not want to do the math, which is fine, but you still have to know. You can't figure it out by using this because we don't have enough information. This doesn't even have time. It's this one that we're going to use. And with that math, we get a time of 1.85 seconds, okay? So that is going to be our time. We figure that out for the y dimension, but if this thing is in the air for 1.5 seconds as it goes up and then comes back down, then it's going to be in the air for 1.85 seconds as it moves left to right. So we just found this time as well. Now that we know this time, well, it's a pretty simple math problem, but actually we can still use the kinematic solver for this. So it's 9.33. Our initial position is 0. We don't know our final position. Our velocity is 9.33, starting and ending because our acceleration is 0, and now we know that the time is 1.85 seconds. And what we're trying to find isn't time anymore. What we're trying to find is final position. It looks like it's going to be about 17.26 meters. So that means that our final position should be 17.26 meters, right? So let's test this. This was with a launch speed of 11 meters per second, an angle of 32 degrees, a height of 6 meters. Let's see where we get. Oh my gosh. We're at 17.26. I'm nervous. What if I'm wrong? Will you judge me? There's 6. It happens to be at 6 meters. What's my angle? 32 degrees. The distance, 17.26. Oh my gosh.
That's Michelangelo.
Should I, what, 26 is closer to 0.3. Okay, here we go. Wait, 13, that's not right. It's 11 meters per second. I gotta change my initial speed. Here we go.
Do it. Oh.
Let's just talk about this for a second. This is nerve-wracking, and this is on film too. My kids are gonna see this. All right, well, oh, look at that. Okay, so you now have seen all the stuff that you need to see in order to make a prediction of an angled launch, which means you've got 3 horizontal launches to think about, you've got 3 angled launches to think about. What I want you to remember is it's not getting it done. I don't care how far you get on this, I just want you to be able to do it. I want you to be able to consistently predict how far something's gonna go. I should be able to give you 3 pieces of information. 10 meters, 17 meters per second, 4 degrees, go. How far is it gonna go? You should be able to tell me. If you get to that point, you are in great shape, all right? And you have the rest of the period to practice. If you have any questions, let me know. Don't forget about homework, don't forget about AP stuff, and let me know if you need any help with anything. Go.